Hello, everybody. Good afternoon, and welcome to our lecture for inorganic chemistry. So hope everybody can hear me and see me well. So hope everything is working perfectly. So today we will continue on our discussion regarding acids and bases that we started on Monday. But before we start or we continue on our acids and bases lecture, some people have asked me about one of the homework questions, which, by the way, I hope everybody is working on it. So the question was regarding question 3 of our homework, which reads, explain the structure of the periodic table, 2 columns on the left, a block of 10 transition metals, a block of 6 on the right, and a pair of 14-member rows below. So this sketch is actually from question 2, not question 3, but I placed it here because it helps us with answering this question 3. So actually, this question 3, maybe it was not so clear what I was asking or like what's the exercise that I want you guys to do. But actually, this is very simple. All that I want you guys to do is to describe how the periodic table is organized. So for example, the 2 columns here on the left, these are the elements of the S block. They are on the S block because their valence shell configuration, so the outermost electrons are in S orbitals. So here we have the alkaline metal and the earth alkaline metals here in this group. The block of 10 for the transition metals. So these are the elements of the D block. Their features are this and this and this, and then their valence shell configuration is this and this and this, and they are organized like this because they have 1, 2, 3, 4, or etc. electrons in their valence shells. The same for the 6 groups on the right. So just say, oh, this is the P block. Their outermost electrons here occupy P orbitals. So here we have the noble metals, the halogens, the chalcogens, and then talk about their electron configurations, for example, and then the pair of 14-member rows below here, which is the lanthanides and actinides group, for example. So this is what I was looking for here. It's just a description of the different groups of the periodic table, okay? Anybody has any questions? All right, so if not, then we can continue on our discussion. So here in our lecture number 4, the idea is to finish our discussion here comprising acids and bases, which makes part of the first section of our course that deals with the chemistry of the elements. All right, so in our class on Monday, we started to discuss several things about acids and bases, and actually we covered definitions and several concepts. We focused on the definitions of Arrhenius in the beginning, and then we focused more on the Bronsted-Lowry theory of acids and bases. So in addition to these definitions and concepts, we talked about some of the important features of Bronsted acids and some of the periodic trends regarding the strength or the acidity or basicity of Bronsted acids and bases. And then we finished, like in the last part, we talked about aqua acids, hydroxyl acids, and oxo acids, which are important in inorganic chemistry. And in this context, we saw that aqueous acid, hydroxyl acid, and oxo acid can be regarded as acids that are produced after successive deprotonation steps. So the aqua acid, in the aqua acid, the acidic hydrogen is present in a water molecule bound directly to the metal site, for example. The hydroxyl acid, the acidic hydrogen is in the hydroxyl group bound directly to the metal. And then in the oxo acid is also in the hydroxyl group bound to the metal, but in this case, we also have an oxo group bound to the metal as well. And then we also saw the reverse approach, in which we discussed basicity and acidity of oxides. So we discussed acidic oxides and basic oxides, and then we saw that this can be an indication of the metallic character of the metal, and then this behavior of the oxides can be an indication on the metal or non-metal properties of a given species. And also, we ended the class discussing amphoterism, in which a species or an oxide can behave both as an acid or as a base. All right, so for today, in order to finish our class on acids and bases in the context of inorganic chemistry, we will discuss the formation of polyoxo compounds, which are very important and have found emerging applications in fields such as catalysis, separation, sensing, among others. Then we will discuss Lewis acidity, or acid and base behavior in the framework of the Lewis theory. We will then, inside the context of Lewis acidity, we will talk about some group properties and important reactions of acids and bases. We will cover some important factors governing interactions between Lewis acids and bases. Then we will talk about the hard-soft classifications of acids and bases, in which hard and soft interactions play a very important role. And then we will finish by including to this theory a more quantitative approach, in which we will mention thermodynamic acidity parameters to discuss acidity and basicity in the terms of this kind of ionic and covalent interactions between the acids and bases. Okay, so let's start with the polyoxo compound formation. So when we have acids containing the OH group, for example, an hydroxyl acid or an oxo acid, this means that these OH or neighboring OH groups between neighboring molecules, they can condense to form polyoxo anions. So a condensation reaction is simply a reaction in which water is eliminated. And we will see an example in the next slide. So this polycation, and then also like the polycation formation from simple aqua cations can also occur with the loss of water. So these polyoxo anions, actually, they are very important because this kind of compounds, it's normally found on Earth or Earth's crust. So several of these minerals are based on polyoxo anions, and they account for most of the mass of oxygen in the Earth's crust. So, for example, when we talk about oxo anions and aqua anions, these species, neighboring molecules, like from this, they can condense or they can react with each other. In the example here of the polyoxo anions, they can form by the condensation between OH groups between neighboring molecules, but actually when two molecules come together, the OH groups can then eliminate water and condensation can occur, but actually this can occur among various neighboring molecules. And the net result is that we have the formation of a inorganic polymer network. So these oxo anions actually can form polymers when the pH is lowered, because this will drive the condensation reaction. And then on the other hand, for the aqua ions, these polymeric species are formed when the pH is raised, because in this case, we are talking about polycations. So here is an example of a condensation reaction between two neighboring molecules here, or two neighboring hydroxyl acids, in this case, in which here we have the OH groups between the molecules. So what happens is, in this condensation reaction, so water is eliminated, and with this there is the condensation or between these species. So what happens is that let me see if I can. So what happens is that the electron pairs from this oxygen attacks the metal, and then this oxygen captures this hydrogen. So there is the formation of this bridge bond between the oxygen and the two centers of silicium here, in this case, together with the elimination of water. And then if we have this process, for example, like if we have two approaching molecules, as I just discussed, we can have this kind of condensation. But then if we have, but actually this can also grow in 3 dimensions if we have OH groups in all these positions. For example, all these neighboring hydroxyl groups can then condense with neighboring molecules, forming this polymeric network or 3D network containing oxygen atoms bridging two of the silicium species in this case. So this is what ends up generating the oxide, for example, in the end. So, going further into this polyoxo compound formation, so if we, for example, have a solution containing aqua ions of metals, for example. So if we have a solution containing aqua ions of metals, and then these metals have a basic or amphoteric oxides, what happens is, as we increase the pH of this solution, so if we are increasing the pH, we are increasing the concentration of OH minus species. So therefore, when we do this, these aqua ions of metals having this basic or amphoteric oxides, generally this leads to the polymerization of these species, as I was discussing, and this polymerization, as it starts to lead to this big and bigger chain of molecules until a precipitate is formed. So precipitation then occurs as this polymeric network grows, and this precipitation can have, for example, applications in the separation of these metal ions, for example, because in this case, when these polymerization via these condensation reactions occur, this occurs quantitatively after a certain pH is reached. So this can be very useful for the separation of metal ions. So for example, except beryllium 2+, which is amphoteric, the elements of group 1 and 2 have no other solution species beyond the aqua ions +1 or +2, for example. So for these species, group 1 and group 2, no other important solution species occur in solution beyond the aqueous ions. And then, of course, when we move to the amphoteric region of the periodic table, then the solution chemistry can become more varied and more rich, for example. So one of these important examples on the formation of these polyoxo compounds are these polymeric species formed by iron 3+ and aluminum 3+ as well, as these species are very common and very abundant on the Earth's crust. So for example, these species, so if we are in acidic conditions, they both have, they exist as the ions in solution, right? So for example, for aluminum, we can write something like this, but when we have the ion in solution, like as we will see in coordination chemistry later on, this actually means that we have the ion coordinated, or the metal coordinated by 6 water molecules, actually. So this is actually the species that we have. So in each position here, we have a water molecule. This should be an oxygen. So this is actually what we have. So what happens when we have, when the pH is increased after, or increased beyond 4, so we increase the concentration of OH- in solution, and this leads to the precipitation of these complexes. So we start to have condensation reactions occurring, leading to the condensation, for example, of the hydroxyl species. So they both precipitate, generating these gelatinous hydrated hydroxides compounds as a result of this change in the pH. So this leads to these precipitated polymers or precipitated polymeric species that are often like have colloidal dimensions between 1 nanometer and 1 micrometer. And then these precipitated species, they crystallize to form stable mineral forms that we end up getting on the Earth's crust, for example. So for example, the extensive network structure of these polymers comprised of aluminum species, they are neatly packed into the 3 dimensions, right? While these iron polymers or iron linear polymer or iron polymeric species adopt more of a linear arrangement. So this is an example on what happens with this aluminum 3+ species. So here we have the initial compound, so the aluminum surrounded by 6 water molecules. So this is the aluminum 3+ present in solution, right? So when we have higher higher pH, we have more basic solutions. So this, the increase in the concentration of OH- drives the abstraction of a proton in the molecule. So one of these waters here becomes a hydroxyl group. And then if this occurs in a larger extent, even more than one hydroxyl group can be formed. So what happens is that they start to generate, so the presence of these hydroxyl groups enable the occurrence then of condensation reactions to occur. So, and then this keeps the network leads to the growth of this network into 3 dimensions, leading to a lot of the formation of this aluminum, oxygen, aluminum, oxygen, aluminum, aluminum, oxygen, aluminum into 3 dimensions until we get, so here is an example of this aluminum, oxygen, aluminum network formation until this extends to a large enough extent so that all the hydrogens are eliminated, and then we are left off with the aluminum oxide. So these are like some of the species formed from these transformations. So when we are talking about oxo anions, the polyoxo anion formation from oxo anions occurs by the protonation of an oxygen atom and then its departure as water. One example of this simplest condensation reaction in oxo anions is an example in which we have the condensation of 2 phosphate molecules in the presence of acid, which leads to the formation of this diphosphate ion, represented here in this picture. So here we have the condensation reaction taking place in this class of oxo anions, for example. And these polyphosphates, actually, they are very important in terms of applications because these polyphosphates are very important biologically, as these species are involved in the storage and release of energy to our metabolism to occur. So, for example, at our physiological pH, which is close to 7.4, the phosphorus entity is unstable with respect to this hydrolysis reaction, right? Or this, so the hydrolysis reaction, which is the opposite of the condensation, right? So hydrolysis is the opposite of the condensation. So at this physiological pH, this entity is unstable relative to with respect to hydrolysis. Consequently, this hydrolysis then serves as a mechanism to provide energy to drive a reaction. So, and similarly, the formation of this phosphorus-oxygen-phosphorus bond can be a means of storing Gibbs free energy. So so the hydrolysis will break this phosphorus entity. So you will release energy because of the bond enthalpies, right? So thermodynamically, this reaction involves energy. So therefore, the hydrolysis provides energy, while the opposite, the formation of the phosphorus-oxygen bond, acts as a way of storing energy. So, and then this is exactly what happens in our body, in which the key to energy exchange in metabolism is the hydrolysis of adenosine triphosphate, which is the ATP molecule, to adenosine 3-diphosphate, as shown here in this picture. So this is the reaction of ATP and ADP to exchange energy during our metabolism. So this polyoxo anions, for example, or these polyoxo anions play a central role in our life and in our metabolism and to controlling these processes in our body. So I mentioned that these polyoxo anions account for the most of the mass of oxygen on Earth's crust, as all the silicate minerals are based on these polyoxo anions, and these species having higher nuclearity formed by the condensation of non-metal oxo anions are typically found as rings and chains. The morphology of these higher nuclearity species, while the silicates are an important example of polymeric oxo anions. And then when we talk about polyoxo anions for the early D-block ions, in particular, when we are talking about D-block ions in highest oxidation states, or early D-block ions in higher oxidation states, such as vanadium, molybdenum, tungsten, niobium, and others, then it's often found in the literature and in the books and the articles the term polyoxometalates instead of polyoxo anions. So these polyoxo metalates have gained like a huge importance in modern inorganic chemistry as well, for various novel applications that arise from their 3D framework structures that are stable to oxidation, for example, and applications of this kind of materials in areas of catalysis and analytical chemistry, for example, have gained a lot of importance. And the framework structure enables different kind of behaviors, such as size selection, for example, and the inclusion of important catalytic sites or redox sites into particular positions, together with the selectivity of size and that can be gained from this well-defined and precise porous structure. So polyoxometalates can then be broadly defined as a polyatomic ion, usually an anion, that consists of 3 or more transition metal oxo anions linked together by a shared oxygen atom to form 3D closed frameworks. So here is an example of the phosphotungstate anion, for example. So here we have the phosphorus, the tungstens here, and here the oxygen species. And here there are several of these species that have been reported, and this is a way of representing this kind of compounds using this shared polyhedra representation, in which the structure of this kind of molecules, or these polyoxometalates, can be drawn by considering different polyhedra sharing corners or edges or faces, for example. So here we have a polyhedra comprised of a tetrahedron of tungsten surrounded by 4 oxygen atoms, in which, therefore, this polyoxometalate can then be represented this way, in which each of these tetrahedron contains one of these unit, and then the oxygen atoms here present here for this species can then be shared among neighboring polyhedra. And then the same for other species, and then you can see that this can become more and more like larger and a bit more complicated as the structure grows in size. So here we have an example of this type of reaction for two chromate ions, in which we have here the condensation reaction generating the polyoxo anion, and here the different ways that this can be represented, showing this representation also based on this polyhedra, so that you guys can see easily here from this molecule that is a little bit simple. And then here an example for a more complex species or a larger molecule. All right, so so for now we have been discussing the acidity in terms of the Bronsted-Lowry theory, which involves reaction in which there is a transfer of a proton between acids and bases. So the Bronsted-Lowry theory of acids and bases focus on the transfer of a proton between species, and then in this context, of course, this is restricted to the transfer of a proton. And in this context, actually, a more general theory of acid and base reactions was introduced by Lewis. And interestingly, Lewis introduced this theory in the same year as Bronsted-Lowry introduced theirs, which was in 1923. So almost 100 years ago. However, this Lewis approach became influential only in the 1930s. So it took a longer time to become accepted or more influential. So the Lewis theory is more general relative to the Bronsted-Lowry and escape these limitations of being restricted to the transfer of a proton to be defined as an acid or a base. So in this case, a Lewis acid, so talking about the Lewis definition, so a Lewis acid is a substance that acts as an electron pair acceptor, and a Lewis base, a substance that acts as an electron pair donor. So here, the Lewis theory focuses on the electron pair. Acids accept an electron pair and bases donate an electron pair. So this, therefore, is really nice and really elegant, and therefore we cannot be restricted to reactions involving transfer of protons. So a Lewis acid can be defined generally by A, and a Lewis base by B, and then B in the base here, so A and B here, just generic letters, and then for the base, we can represent here the electron pair to emphasize that the base will donate the electron pair, while the acid will be the receptor of the electron pair. So the fundamental reaction of a Lewis acid and base is the formation of this complex or adduct AB, in which the acid and the base bond together with each other by sharing the electron pair that is supplied by the base. Such a bond or such a fundamental reaction generates this AB entity, and such a bond is often called a coordinate bond between these acid and base, in this Lewis acid and Lewis base species. So the bonding between a Lewis acid and a Lewis base, which is the donation of this electron pair from the base to the acid, can also be viewed in terms of the molecular orbital theory. So if we don't need to go into a lot of details about the molecular orbital theory, but basically it means that here we have the acid and here we have the base. So molecules of the acid and the base here have orbitals or molecular orbitals, and these molecular orbitals are generated by the combination of the atomic orbitals of all the elements that comprises the molecule. So in a molecule, the orbitals of the individual atoms combine together to generate molecular orbitals or orbitals of the molecule, or orbitals that are therefore extended over the entire dimension of the molecule. So when we have the acid having its molecular orbitals, for example, and here the base with its molecular orbitals, so we feel these molecular orbitals the same way that we feel atomic orbitals with 2 electrons per orbital, for example. And then when we form a bond between the acid and the base, it means that the orbitals of the acid and the base combine together here to form this coordinated bond, or this AB or acid-base complex. And then in this kind of bond, for example, this orbital of the acid is occupied by 2 electrons, and this orbital of the base is occupied by 2 electrons. So the combination of 2 orbitals generate 2 other orbitals for the molecule or the complex, and then each has 2 electrons, because we have a total of 2 orbitals now and 4 electrons, 2 from the acid and 2 from the base. The same thing happens for this one. And then here, as the base has a lone pair, actually what happens is that here we have now the frontier orbitals or the valence orbitals for the molecules or for the species represented here. So LUMO refers to the lowest unoccupied molecular orbital, and the HOMO refers to the highest occupied molecular orbital. So here the base has a lone pair, so it has a pair of electrons in the HOMO, and the acid is the electron acceptor, has an empty LUMO. So when these orbitals combine, 2 molecular orbitals are generated. And then also always when we have the combination of 2 orbitals to generate molecular orbitals, what happens is that 2 orbitals will combine to generate 2 other orbitals in the molecule. So we always generate a molecular orbital of lower energy and a molecular orbital of higher energy. So we have in-phase combination and out-of-phase combination. And for this orbital, the overall energy is decreased. And for this orbital, the overall energy of the system is increased. And then, of course, the average remains the same of the original orbitals. So what happens here, because we have only 2 electrons, they occupy this in-phase combination of molecular orbitals, or they occupy only the molecular orbitals that had their energy decreased or stabilized relative to the original orbitals that were combined. So this kind of orbital is called bonding orbital, and this kind of orbital in which the energy is raised is the anti-bonding orbital. So what happens is that this process, because electrons occupy only the bonding orbitals or only the orbital in which the overall energy of the system is lowered, this means that as a result of this acid-base interaction, there is a lowering of the overall energy of the system when the bond is formed. So this is like the description of this acid-base interaction by Lewis forming this complex or this coordinative bond. So this is why it happens from the point of view of molecular orbital theory, because there is a net lowering of energy because the electron pair occupy only the bonding molecular orbital and the anti-bonding molecular orbital is left unpopulated. So let's talk about, like, to make it clearer, some examples of Lewis acids and bases. So for example, a proton is a Lewis acid because it can receive an electron pair. As in the formation of the ion ammonium from ammonia. So here, what happens is that ammonia has electron pairs here, and then these pair of electrons is donated to the hydrogen species, and then the hydrogen receives the electron in the formation of ammonium from ammonia. So, and then actually we have the Bronsted-Lowry theory of acids and bases and the Lewis theory of acids and bases, but actually they are all acids and bases. So like any Bronsted acid, as it provides the protons, they exhibit Lewis acidity too, right? Because like when we have the donation of a proton, so the proton is eliminated from the molecule. So when the proton is eliminated from the molecule, it means that the electron pair of the bond containing the hydrogen atom is then received by the neighboring atom. So a Bronsted acid also exhibits Lewis acidity too. So we say that a Bronsted acid exhibits Lewis acidity rather than a Bronsted acid is a Bronsted base. And now the same thing for the bases. So rather than a Bronsted acid is a Lewis acid. And the same from the bases, because a species that receives a proton is also an electron pair donor, because to receive the proton, the species has to donate an electron pair. So for example, ammonia is a Lewis base as well as a Bronsted base. And one of the advantages of the Lewis definition is that the proton is not essential. So we are talking about only the electron pairs, right? So a wider range of substance can be classified as acids or bases based on the Lewis theory. And also, in addition to all of this stability of the complex or this acid base unity can also be strongly influenced by steric interactions between the acids and bases. So the interactions of the groups bound to the atom on space. All right, so a molecule with an incomplete octet or valence electrons can complete its octet by accepting an electron pair, such as in this case. So here, this species is an acid because it receives the electron pair from the ammonia molecule, and here the ammonia is the base forming this type of adduct, which is the AB adduct that we were talking about before. And a metal cation. So I mentioned that a metal cation in solution here, cobalt 2+, is actually represented by the metal coordinated to 6 water molecules. So a metal cation can accept electron pair supplied by the base in a coordination compound. So here, in this case, when we talk about these species, this is also an example of acid-base interaction in the framework of Lewis, because cobalt here accepts electron density or the electron pair from water. So water acts as a base to bind to cobalt. So this generates this acid-base adduct as well. So the interaction here in this coordination compound, this can also be represented as being formed as a result of acid-base interactions, in which the cobalt is the Lewis acid and the ligands here, water, become the Lewis base. And then in addition to forming these acid-base interactions to complete the octet, a molecule or ion with a complete octet also may rearrange itself or its valence electrons to accept an additional electron pair, in which the molecule or the ion may be able to expand its valence shell or be large enough to accept another electron pair. And one example of this is the formation of this complex, in which silicium is coordinated to 6 fluoride ions, and then here fluoride ions act as the Lewis bases, in which, starting from the species containing 4 fluoride ions, this additional fluoride can also bind to the silicium atom to generate the species with 6 atoms with an expanded valence shell. So this can occur in some cases, and this is common for halides of the heavier p-block elements, such as those described here. All right. Okay, so before we continue, let's then take a 10-minute break. So should we be back at 1:03? Is that okay? All right, so I will see you guys at 1:03.
It's 1:02 right now.
Okay, 1:13. I'm sorry, 1:13. Is that okay? All right, I will see you guys at 1:13. Hello, so welcome back, everyone. So continuing our discussion, so we discussed here the definition of acids and bases in the framework of Lewis, and then we gave a little bit of some examples to you of Lewis acids and bases. And then now let's take a look at some characteristics of Lewis acids, for example, according to the group in which the elements belong. So let's take a look at some group characteristics of Lewis acids and bases as well. So let's talk about first the S-block elements. So let's talk about Lewis acids and bases of S-block elements. So alkali metal ions, so group 1 of the periodic table in the S block, they act as Lewis acids in water, forming the hydrated ions. And these alkaline metal ions, they do not act as Lewis bases. So they only act as Lewis acids. Regarding group 2, the beryllium atom in beryllium dihalides. For example, here we have a beryllium with 2 halogen atoms here. So that's here for halides. So beryllium atom in dihalides acts as a Lewis acid. And this occurs by the formation of a polymeric chain structure in the solid state, as represented here in this molecule. So this extends in both directions to generate this polymeric chain structure. And here a sigma bond is formed when the lone pair of electrons of the halide ions, which acts as a Lewis base, is donated to this empty sp3 hybrid orbital on the beryllium atom. So the beryllium atom acts as an Lewis acid, receiving the electron pair from the halide ion acting as the Lewis base. So now group 13, which is the group for boron, for example. So when talking about boron, the ability of these boron 3 halides, which is an important class of compounds for this group 3 Lewis acids. So the ability of these boron 3 halides to act as Lewis acids generally increase in the order that when of the fluorine being smaller or less, or a smaller tendency to act as a Lewis acid than the chlorine, and is smaller than the tendency of the bromides. So these planar molecules, so the 3 halides of boron and also the 3 halides for aluminum, they have incomplete octets, which means that they have vacant p orbitals perpendicular to the plane of the molecule, which therefore, in principle, can act to accept a lone pair from the Lewis base, right? So here in the central atom, this molecule is planar. So we have here the 3 halide happening like on a plane. So here is a trigonal arrangement, and this here in the boron or in the central atom, we have empty p orbitals perpendicular to the plane of the molecule that can accept the electron donation from the base. And the trend is the fluorine has a lower acidity than the chloride and the bromide. And actually, this order of acidity is the opposite to what we would expect just based on the electronegativities of the halogens. And this order of acidity is expressed by the order of thermodynamic stability of the complex between these 3 halides with a base, such as this species. So the thermodynamic stability, the higher the thermodynamic stability here indicates that the acid-base interaction is more favored, as if we have a strong acid-base interaction, the energy of the system will be lower to a larger extent, so we will have more thermodynamic stability. So here indicates that the acidity of the 3 fluoride is lower than the 3 chloride and lower than the 3 bromide. Okay, so this order is the opposite to what we would expect relative to the electronegativities of the halogens. Because if we have this molecule, for example, here, which is planar, with the halogens in these positions, And then the acidity comes from this empty p orbital perpendicular to the molecule. So this p orbital will receive, this p orbital is vacant, so that it will act receiving electron donation from the ligands. So what happens is that we would expect that as the halogen becomes more electronegative, as the halogens become more electronegative, the halogens can attract the electron density from the central atom, from boron. Therefore, if the halogen is more electronegative, it means that the boron atom becomes more electropositive. So it becomes more deficient in electrons, and therefore the electron density or the acidity here in this case by Lewis would be highest because it's more deficient in electrons. So the stability, thermodynamic stability when receiving electrons would be higher. So this is the trend that would have been expected based on the relative electronegativities of the halogen. So in this case, this electronegativity argument would therefore suggest that fluorine, being the most electronegative halogen, should leave the beryllium atom or the central atom most electron deficient, therefore having the highest Lewis acid behavior, or be able to form a strongest bond with an incoming base, right? So here we do not observe this trend, so we observe the opposite trend actually based on this electronegativity argument. This is because actually what happens in these three halides, as shown here in this picture, the halogen atoms in these boron 3 halides, they can actually form some pi bonds or bonds perpendicular to the plane of the main bond here between the atoms. So the halogen atoms form pi bonds with the empty 2p orbital in the central beryllium atom. So the halogen atoms here, they have filled p orbitals perpendicular to the bond axis. So here we have the formation of p bonds or p donation from the halogen to the central boron atom. And then for the interaction or for the formation of an acid-base adduct in which these orbitals receive electron pair from a base, this requires that these pi bonds between the central boron atom and the neighboring halogen should be disrupted so that these orbitals then are available for the formation of the complex or the bond with the neighboring base. And then this pi bond also favors this planar structure of the molecule, which is a structure that must be converted to pyramidal in order to form the acid-base adduct. So what happens is that even though the fluoride atom is the most electronegative, it is also the smallest. So it's the one that forms the shortest bonds here, in this case, in the molecule. And then because these atoms are in more proximity to the beryllium atom, in this case, this enables that the fluoride atom also forms the strongest pi bonds with this empty orbital of the beryllium atom. Therefore, as fluorine forms the strongest pi bonds, then this orbital becomes less electron deficient, or it becomes harder or less favored for this orbital to act as a, or this species to act as a Lewis acid, receiving electron donation from the base through this orbital. So the pp pi bonding is strongest for period 2 elements like the beryllium, largely on account of the small atomic radii of these elements and the significant overlap for these 2p orbitals. So in this case, the beryllium 3 fluoride has the strongest p bond, or the strongest pi bond that needs to be broken when the amine or na base will form this acid base or nitrogen beryllium bond. Therefore, this is why in this case, this species has the lowest acidity, because therefore, due to this pi interaction between with the halogen atoms, in this case fluoride, this empty orbital becomes less available for interaction or to receive electron donation from a base forming an acid-base adduct of Lewis. So in terms of applications, this boron trifluoride is widely used as an industrial catalyst to extract bases bound to a carbon and is to generate carbocations, as represented here by this chemical equation. Aluminum halides occur as dimers in the gas phase. Aluminum chloride, for example, has this molecular formula. And then when we are talking about aluminum chloride, in terms of applications, it's widely used as a Lewis acid catalyst for organic reactions, such as Friedel-Crafts alkylations, which refers to attachment of a R plus species to an aromatic ring. So here is the explanation. So this species forms an adduct with aluminum chloride, which then leads to the attachment of this species to the aromatic ring, and also for acylation reactions. So it's very important in driving these organic reactions. Now, going to the group 14, the elements in the group 14, other than carbon, has exhibited hypervalence, which is the property or the capability to expand their octets and act as a Lewis acids by becoming 5 or 6 coordinates. So this, the example of the silicium atom with 4 fluorines, then accepting even more electron density to have the silicium atom bound to 6 fluorine species, as we discussed previously, is an example of that. So the tin chloride in group 14 can act both as Lewis acid and a Lewis base. And unlike carbon, the silicon atom can expand its valence shell, or simply to become large enough to become hypervalent. So some stable structures with 5 coordinated trigonal pyramidal geometry are known, as shown here in this picture. So we have 5 bonds here around the silicium atom, so it's 5 coordinated. And then here we have acid-base interactions in which the silicium is seen as an acid, a Lewis acid, and the ligands here as Lewis base, donating electron density to the central silicium atom. And here is the example that we saw previously, in which the formation of a 6 coordinated species can be formed when the Lewis acid, this tetrafluoride, the silicium tetrafluoride, reacts with 2 other fluorine ions, in which we can have the expansion of the valence shell. And then the germanium and tin fluorides also can react similarly. And then when we are talking about the acidity for these species, or the tetrafluorides of silicium, we have this trend in which the fluoride has a higher acidity than the chloride, then the bromide, and then the iodine. And this, in this case, correlates with the electronegativity or with the electron withdrawing power of the halogen. So this was the reverse that we saw with the three halides of boron. And in this case, we have that the electronegativity effect plays the major role. So the more electronegative is the atom, the more electron deficient the empty orbit, the central atom becomes. So it's easier, or it becomes a better receptor of a better Lewis acid because it forms more thermodynamically stable adducts when it interacts with a base. Okay, so regarding the tin chloride, it can act both as a Lewis acid and as a Lewis base. So as an acid, the dichloride can combine with another chloride ion to form the trichloride species as shown here. And then as a base, this species can then donate the electron pair to a Lewis acid, such as another metal, for example, generating these compounds having metal-metal bonds, as shown here in this example. So when we talk about tin-4 halides, in this case, they act as Lewis acids, reacting with halide ions to form species with 6 ligands, as shown here. And this is similar to the example for silicium that we discussed earlier. And then here, the strength of Lewis acidity also follows the trends in electronegativity of the halogen atom present in this species. So the trends in electronegativity, electron withdrawing capacity of the central atom. So the central atom becomes more electron deficient. And as the central atom becomes more electron deficient, it then becomes our strongest Lewis acid. So going to the group 15 now. So the oxides and halides of the heavier group 15 elements act as Lewis acid. So the phosphorus pentafluoride is a strong Lewis acid and forms complex with ethers and amines. The heavier elements of the nitrogen group form also some of the most important Lewis acids. And these species, for example, being one of the most widely studied compounds. For group 16, sulfur dioxide can act both as a Lewis acid and a Lewis base. Its Lewis acidity is illustrated by the formation of a complex with 3-alkyl amine, which acts here as a Lewis base. So this is the kind of adduct that can be formed in this case. And acting as a base, sulfur dioxide can donate either lone pairs from the sulfur of oxygen atoms to a Lewis acid. And then this is an example of this species acting as a Lewis base, here donating electron pair from the sulfur atom to a ruthenium species or a ruthenium metal, acting here as the Lewis acid. When we talk about the sulfur trioxide acts as a strong Lewis acid and a very weak Lewis base. The acid, Lewis acid behavior can be illustrated by this kind of reaction, forming this adduct with an amine, for example. When we go to group 17, Lewis acid, so bromide and iodine act as mild Lewis acids. The 3-iodide ion is an example of a complex and an allied base. So a complex between the molecule and the allied base, for example. And these kind of acid-base reactions in the framework of Lewis that we are just discussing, or that we have just discussed, they have widespread use in chemistry, chemical industry, in biology. So when we talk about the topic of CO2 capture, for example, which is extremely interesting and extremely being researched nowadays in the context of mitigating climate change and also turning CO2 from a waste into the commodity, because, you know, like, we not only have to remove the CO2 from the atmosphere, but another approach is to also use the CO2 as a starting molecule to make other important molecules, such as fuels or platform molecules for the chemical industry. So approaches to mitigate climate change or the most cutting edge approaches to mitigate climate change involves the use of CO2, or to shift CO2 from a pollutant or from a waste into a chemical commodity in which CO2 can act as a starting material to make fuels, for example, methanol, ethane, propane, other types of molecules that are interesting for the industry. But in any case, one of the main steps to make this happen is to capture CO2 from the atmosphere. And this capture of the CO2 is also very important, like for industries, for example, that don't want to release CO2 for the atmosphere, or has several applications in this case as well. So one of the approaches to capture CO2, either to avoid the emission of CO2 or to use this CO2 from the atmosphere to another, to a chemical reaction, for example. So one of these, the ways that this is done is through an acid-base interaction in which CO2 reacts with an amine, forming this kind of adducts, right? In which the amine acts as the base and the CO2 as the acid. And another important example is the toxicity of carbon monoxide in animals. This is also an example of acid-base interaction, because in animals, or in us as well, hemoglobin is responsible for transporting oxygen in our bloodstream, and then hemoglobin contains an iron 2 center. So in this case, the transport of oxygen happens because oxygen forms a bond with the iron 2 species in the hemoglobin molecule. And this is an example of acid-base interaction in which the iron species acts as an acid, Lewis acid, and the oxygen as a Lewis base. And then this interaction is reversible in this case. So that's why this molecule can transport oxygen. But then, for example, if we inhale CO or carbon monoxide, it's toxic, because carbon monoxide is a much stronger or a much better Lewis base, not acid, base than oxygen relative to the iron in the hemoglobin molecule. Therefore, it will form a much stronger bond with the iron, which is basically almost irreversible. So this poisons or blocks these iron 2 sites, and then therefore hemoglobin molecules do not become able to transport or to bind and transport oxygen anymore. So that's why it is toxic. And all the reactions involving metal atoms of the D block forming coordination compounds that we will see in more detail later in the course are all examples of acid-base interactions. So the formation of this kind of coordination compound, for example, nickel with 6 amine ligands. So this is an example of acid-base interaction in which the metal cation acts as a Lewis acid, and the base in the amine molecules here acts as a Lewis base. So let's now take a look at some classes of important reactions of acids and bases in the Lewis framework. So the simplest reaction that we have been talking about here is the complex formation through this coordinate bond, or the acid-base adduct. So the simplest acid-base reaction in the gas phase is the complex formation between the Lewis acid and the Lewis base that we have been discussing so far. So in this complex formation, a free Lewis acid and a free Lewis base become linked by a coordinate bond, as represented here. For example, another important reaction of Lewis acids and bases are displacement reactions, in which an acid or a base drives out another acid or base from a Lewis complex. So Lewis complex here refers to this acid-base adduct. So this displacement reaction then can be defined as the displacement of one Lewis base by another, right? Changing the nature here of this adduct or this complex. And here we have an example in which this base then displaces this base in this base acid adduct. So this is a displacement reaction. And then this can also happen with the acid. So the displacement of one acid by another, in which we have the same thing happening. So we have here an acid-base adduct, and then we have a new acid that displaces the original acid present in the molecule. And here we have an example in which the boron trifluoride, acting as an acid, displaces a nitrogen atom here in this complex. Another example of reaction is the metathesis reactions, which involves a displacement reaction, which is assisted by a formation of another complex. In other words, it's a double displacement reaction in which there is an interchange of partners. So we have one acid-base adduct reacting with another acid-base adduct, leading to this interchange of acid-base pairs here in the molecules, as exemplified by this equation. So the proton was the key electron pair acceptor in the discussion of Bronsted acids and bases. When we discussed Bronsted, the strengths of Bronsted acid and bases. When we are considering Lewis acids and bases, we must allow for a greater variety of acceptors, because we are talking only about the electron pair, and more factors influence these interactions between electron pair donors and the electron pair acceptors in general. So in this case, for Lewis acids and bases, these hard and soft classifications of acids and bases become very important and become very useful to identify the strengths. So these definitions of acids into hard and soft species this is totally empirical. And this is based on the measured trends in instabilities of the complexes or the acid-base complexes in the Lewis framework that they form. So this so it's based empirically in the trends or instabilities of the complexes that they form. And then the result of these observations is that species classified as hard acids tend to bind with greater stability to species classified as hard bases, and soft acids to soft bases. So these classifications of substances as hard or soft was introduced by Pearson, and it's a generalization of the distinctions between two kinds of behavior that were named originally as class A and class B, for example. So these two classes, hard or soft acids or bases, so they were identified empirically by the opposite order of strengths. So basically, it was measured by the equilibrium constant for the formation of a complex with which they form complex with allied ion bases. So for example, hard acids were classified as species that form complexes with stabilities that are in this order relative to these halides. And the soft acids were classified as species that form complexes with stabilities with the halides following this trend. So in other words, the soft acids bind more strongly to iodine and less strongly to fluorine, and the hard acids form more stable complexes with fluorine than with iodine. So it was based on the stability of the species with these different halides. So this constant formation or disequilibrium constants increase steeply, for example, from fluorine to iodine when the acidic mercurium 2 is treated. So here we have mercurium 2 plus, and here we have the values of the equilibrium constant or formation constant, and here the different halogen atoms. So for mercury, for example, stability increases, or the constants increase when we move from fluorine to iodine. So according to this, it becomes softer. So mercury is a soft acid. So the trend is less steep, but goes into same direction for lead, which indicates that this is a borderline soft acid. The trend is opposite direction for zinc, indicating that it's a borderline hard acid, and the downward steep slope for aluminum indicates that this is a hard acid. And so this is, it's based on a trend that was determined empirically, but we can see that small cations, which are not easily polarized, are hard, and then they form complexes with greater stability when the anions are also small, while large cations are more polarizable, and they are classified as soft, and they form more stable complexes with species that are also more polarizable. So hard acids tend to bind to hard bases in which the interaction is predominantly more ionic character, and soft acids tend to bind predominantly to soft bases in which the character is predominantly covalent. So a similar classification can be applied to molecular acids and bases, and acids are identified as hard or soft by the thermodynamic stability of the complex that they form, as set out for the allied ions, and for other species as follows. So we can also choose other species which are neutral molecules in this case to do this classification. So hard acids also form complexes with the stability in this order for these molecules, and soft acids increased instability in this order. So this is all done empirically. And in the end, we can have these tables classifying acids and bases into hard, borderline, and soft, which can give us important insights into understanding the stabilities and the tendencies in reactivity, for example. So the interpretation of hardness is that the hard acid-base interactions are predominantly electrostatic, while the soft interactions are predominantly covalent, and the bonding between hard acids and bases can be described in terms of ionic or dipole-dipole interactions, and soft species are more polarizable, and in this case, they have a more prevalent covalent character. So these interactions help us to systematize complex formation, is useful to choose in preparative conditions, predicting the direction of reactions, and helping to rationalize the outcome of metathesis reactions in which hard, soft interactions will be favored. But of course, this also has to be used with care, as other factors can also play a role. And also this classification helps us to understand the terrestrial distribution of the elements and the types of compounds that they form, as we discussed in the first in the first lectures. Also, for example, like hard cations are found in association with hard bases and soft cations with soft bases. So an important alternative to this hard-soft classification is based on more quantitative parameters, such as thermodynamic acidity parameters, which is an approach in which electronic effects, structural arrangement, and steric effects are incorporated into a small set of parameters to describe the stability of the atoms that are formed. So if we consider this complex formation, the standard reaction enthalpy for this reaction can be reproduced by this Drago-Weyland equation, in which these factors E and C represent electrostatic and covalent factors, and they actually accommodate all factors except solvation. And this equation is semi-empirical, but it's very successful and useful across a wide range of reactions. And there are a lot of tables for these electrostatic and covalent species for different species. So that can be useful to use to do these predictions. And these can provide estimates of enthalpies of complex formations for over 1,500 complexes, and they can be combined and to calculate enthalpy. And these enthalpies can be combined together to calculate enthalpies for displacements and metathesis reactions as well. So with this, we finish our discussions of acids and bases in the framework of inorganic chemistry of our course here today. So we discussed several definitions and concepts. We discussed the features of Bronsted acids and bases and some periodic trends. We discussed simple oxoacids, anhydrous oxides, polyoxo compound formation. We discussed today Lewis acidity, group properties, some important reactions, and factors governing interactions between Lewis acids and Lewis bases. And then we finished with these hard-soft classifications of acids and bases, and we discussed some thermodynamic acidity parameters. So with this, we finish our class today, and next week we will be focusing on oxidation and reduction. So does anybody have any questions before we finish for today? So if not, I will post these slides now to our Moodle page, as well as the video of the lecture. And then I will see you guys again on Monday. And on Monday, I will also post homework 2 to our Moodle system. And then homework 2 will cover acids and bases. All right. So thank you very much, everyone. Have a great weekend. And I will see you on Monday. Bye-bye.